Okay, so we're working on our new chapter here, chapter 10, where we've got stuff that's moving around in circles. So we have a new position symbol, which is going to be theta. We've got omega, which is velocity. We've got alpha, which is going to be acceleration, and we'll talk a little bit more about that in a couple minutes. We've got time. We talked about how we determine the directions of the vectors for omega and alpha by using the right-hand rule. And so you're curving your fingers naturally in the direction that that object is turning or accelerating. And the thumb of your right hand, when you stick it out, tells you what direction the vector's in. We talked about how theta isn't really a vector, because it doesn't obey the commutative property of vector addition, but we can still talk about it as being positive or negative. We talked about how quantities that move counterclockwise are positive and quantities that move clockwise are negative. This is one situation where you don't get to choose. Okay, they are what they are. We also talked about the three formulas that we have that relate all of those things to each other. They are identical to the chapter 2 equations that we had a million years ago, except that they have thetas and omegas and alphas instead of x's, v's, and a's. And we'll talk about today, I think, the relationship between the rotational quantities, which are this, and the translational quantities, which are the ones we had in chapter 2. So we had started a problem, and we got through the first half of it. So we were working on page 288, number 14. And we did A and B, which meant that we found out what alpha was. So we have this wheel. It's starting from rest. It's spinning up. Eventually, it has an omega of 10 revolutions per second. 60 revolutions later, it's going faster at 15 revolutions per second. And part A was to find the angular acceleration, which is good. And what was the angular acceleration? Yep. And then you had to find the time between when the wheel was going 10 revolutions per second and 60 revolutions later when it was going 15 revolutions per second. And I don't really care what that time was, because that doesn't really affect what we're going to do with C and D. However, the acceleration is constant for the whole time the wheel is turning, so we might use this alpha again. So can somebody read what we're supposed to figure out in C and D, please? Okay, so we're looking at a different part of the wheel turning now. We're looking at the wheel starting at rest and speeding up to 10 revolutions per second, and we want to know how long that took, and we want to know how many revolutions it went through to get there. So we need to change our list of knowns again. So we talked about how drawing a picture is not exactly the most useful thing in the world, because basically you just have things that move around in circles. But we do still have a list of quantities that we can use to help us solve the problem. So somebody give me something I can put on my list of knowns. Okay, so we'll let the initial position be 0. What else? Yeah, because it starts from rest. Good. What else? Yeah, because the acceleration of the wheel is constant, so it doesn't matter what time interval I'm talking about. At this point, it's just acceleration. At this point, it's the acceleration that speeds something up or slows it down. I'm going to talk about that in a couple minutes, the two different kinds of acceleration. There's one more piece of information that we have here. It's going to be 10 revolutions per second for both, because I want to know the time it takes to get there and the number of times the wheel turns to get there. Okay. So for part C, what's my find statement going to be? Okay. So we're going to look back at our formulas that we wrote down when we had class last, which I think was Monday. And what's my formula? That looks like a good choice. Dilemma without position, and we don't have the position. So T is going to be omega over alpha, or 10 revolutions per second divided by 1 revolution per second squared. So how long is this going to take? 10 seconds. Right? We good? If this was motion happening in a straight line, you could solve this in your sleep. Okay, it's really not that much harder. It's just you got to adjust to the new symbols. And you kind of have to, for most of this, you kind of have to abandon the visualizing, which is hard, I know. And that's why you've got to go back to thinking about how it worked when you were doing chapter 2 and take a leap of faith that it'll work out. All right, so how about part D? What's my find statement for part D? No, I don't want, I already know what omega is. Theta, I need to find theta. I need to know how many revolutions we're going to go through. So what formula am I going to use now? Okay. I admire that you're using a formula that doesn't have t. And there's a lot of things we can get rid of because we know that omega 0 is 0 and we know that theta 0 is 0. I was going to use theta equals theta naught plus omega naught t plus 1/2 alpha t squared, but it doesn't matter. I applaud that you chose not to use something you calculated in case you messed it up, which is what I always taught you to do. So theta is going to be omega over 2 alpha, if I did my algebra correctly. So that's 10 revolutions per second squared divided by 10 times 1 revolution per second squared. And what's that going to give us? You do not need your calculator. $50, good. And what's my unit here? Revolutions. Okay. So this was supposed to be a pretty straightforward kind of plug and chug just to get us used to the symbols, used to the formulas again. All right. And I'm sure there are homework problems like this. What's up, Siri? What formula did you use? That's the one I used, and I got 52. Let's look real quick. Okay, so theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. So that's 0 and that's 0, right? So alpha, there you go. Okay, so there's going to be some kind of a relationship between our new rotational quantities and our old translational quantities. So we want to talk about that for a couple minutes. And in fact, we already introduced one of these, which was S was equal to theta R. And we talked about that when we actually defined what theta was and how it related to an arc length that a point may have moved through. Okay? And remember again that we have to have theta in terms of radians. So in chapter 2, how would I have gotten a velocity out of that formula? R is the radius, which is a constant, probably. Yeah. How do I get velocity from position? I take the derivative, right? So I'm just using S here for position because if I use X, it looks a little weird because I'm not necessarily moving along the X-axis. So we need to use a different letter. And so if we assume that we have a rigidly rotating body that's symmetrical, then R, which is that distance from the center out to wherever my particle is, that R is going to be the same. So the only thing that's going to change is d theta. And then what do you think d theta dt is going to be? No. Not radial velocity. Radial velocity would be going in and out towards the center or away from the center. It's how theta changes. And what do we call the velocity when the thing moves around in a circle? No. If ds dt is v, yeah, rotational what? And what's my symbol for rotational velocity? Omega. So this is equal to omega r. It's like pulling teeth. Make yourself flashcards. You gotta learn it. So V is equal to omega r. Yeah. Okay. So remember that we are talking about rigidly rotating bodies, which implies that the parts of the body don't move with respect to each other. Okay. So we talked about how an empty water bottle, when it rotates, is a rigidly rotating object. But if I put water in there, not so much. Okay. A marker is a rigidly rotating body. A bike wheel, as we will talk about very often, is a rigidly rotating body. Okay. But if we keep all of this in mind, and here's, for instance, my bike wheel with the spokes. Okay, and that bike wheel is going to rotate around its axis of rotation in the middle. And also remember that for a rigidly rotating body, all parts have the same what? No, no. What kind of velocity? Omega. Okay. I am so happy that my class is, waking up and engaging. So, every part on here has the same omega. Takes the same amount of time for every part. Whoops. Whether I'm talking about my green dot here that's about halfway out, or my black dot here that's all the way out. Okay? Those 2 points have the same omega. Takes them the same amount of time to make a complete trip around the circle. So, correct. Our solar system is not rigidly rotating because the parts actually interact with each other and pull on each other. Okay. But what's different for my 2 positions? Yes. They are at different distances from the center. So what that means is that they make different size circles with different circumferences. But remember, if they have the same omega, they have to go all the way around that circle in the same amount of time. So which dot goes faster? The outside one. So my black dot has a greater linear velocity than my green dot. So they're both going to go around, and this is the part that should make your mind freak out. They're both going to take the same amount of time to go around, but the black dot moves faster than the green dot. It wasn't a Calvin and Hobbes. And the father makes Calvin's brain pop. And he sits up all night worrying about it. That's a physics nightmare for you to have, Priya. Maddie. Correct. Because at the moment, we are only talking about objects that are spinning. We are not talking about objects that are rolling. That's chapter 11. And a whole nother layer of complexity that we're not ready to deal with since we can't identify omega and theta at the moment. Okay. All right, we good? We got it? Important foundational work here that's going to come back. All right. So, because these objects are rotating, they're undergoing cyclic motion, they keep coming back to the same spot. Okay, you've probably seen me with my bike wheel that has the tape on it. I'm not going to get it out today, but every time that bike wheel comes around and every time that piece of tape comes back up to the top, it's made a whole circle. Okay, it's gone through one cycle. So because of this, we frequently talk about a period, which is capital T. So again, please make sure that when you're taking your notes and doing your problems, it is abundantly clear to me what the difference is between a capital T for period and a lowercase t for time. Okay, that's my whole, there's a little hook on my time. Okay. So the period is going to be the amount of time for one revolution. So if I assume for a moment that my object is moving at a constant speed, which I don't necessarily have to, but we'll just build it out of here. Okay. Then that velocity, that linear velocity, is the distance my object travels divided by the amount of time it takes to travel, right? Right? So if I'm talking about one period as the amount of time that I travel, how far does my dot go in one period? Circumference. Yes, but I'm not worried about displacement right now. That kind of becomes a nonsensical thing to talk about because the object just keeps going around and around and around and around and around. And in this case, we are very concerned with how many times it goes around. So, make me proud. What's the circumference of a circle? Yay! Over t, because that's my symbol for period. Okay. And I can turn this around and solve it for period, and I get 2 pi times r over v. I sincerely hope we are beyond the point where somebody's going to ask me why I don't have to have a line under everything and I can just make it r over v. But you might ask me what philosophical omniscient narrator reason I had for writing it as r over v. Because what's r over v going to be? 1 over omega. So this becomes 2 pi over omega. Or omega is equal to 2 pi t. Okay, and this too will come back in the last chapter that we do. I think it's chapter 15, where we talk about frequency and stuff. Okay, so you with me? You got it? The period shouldn't be too new because we've done period before. Okay, we're just relating it now to omega. And you can also think about it, if you like, if we want to talk about the angular distance that we go through in one period, how much is that going to be? Yes, but I don't use degrees, I use what? Radians. So how many radians? 2 pi. So I can also say that omega is 2 pi over t, and get it the same way I got v was equal to 2 pi r over t. And of course, these two equations are the same. All right? We good? We rocking? Okay, because angular speed would be the angular distance I traveled divided by that amount of time. Okay? All right. What? Yep, 2 pi radians, but I don't need radians, they just go away, remember. They're just an indicator rather than a unit. Oh, because I wrote it wrong. Yeah, that's wrong. It looked unfamiliar, so erase that, everybody. Sorry about that. And thank you for pointing out that I did my algebra wrong in my head. All right, so have we found all my mistakes? Shows you're paying attention. I'm all right with that. All right, so let's move on and talk about acceleration. And remember that I have an expression for velocity. So how do I go from an expression for velocity to an expression for acceleration? What do I have to do? Take the derivative. So a is going to be dv dt. Remember that v is omega r. hang on. Remember again that if I'm talking about a rigidly rotating object, then r, the distance between the point that I'm interested in and the rotational axis, is going to be a constant because the points don't move with respect to each other. And so what do you think d omega dt is going to be? Alpha. So that's going to be alpha r. But as I alluded to earlier and Zoe was asking about, we have to be careful because there are two kinds of acceleration. There's the speeding up, slowing down kind. Not kid. And there's also the change direction kind. And this is the acceleration from chapter 2. And the change your direction kind is the centripetal acceleration from chapter whatever it was, 5, 6, 4. All right. So the acceleration from chapter 2, which we're going to call a t because it's the translational acceleration, that's the thing that's going to be equal to alpha r, because that's what's going to have to do with the wheel or whatever the object is speeding up or slowing down. And that's how we used it in the previous problem. It was making the wheel go faster and faster. Now, the other kind of acceleration is our good old friend AC, centripetal acceleration. I'm going to call that AR because it points radially inward, as a matter of fact. If you call it AC, it's not going to be a big deal, but it points radially inward, okay, towards the center, towards the axis of rotation. What's everybody's favorite formula for AC? V squared over R. However, if I want to relate this back to my angular quantities, what's V equal to? Not just omega R squared over R. I can cancel one of my R's and get AC is equal to omega squared R. And I think I did the algebra right that time. Okay, or we should also add that this is AR. It's equal to AC. And as we'll talk about much later, I can have both of those accelerations happening at the same time. I can have an object that's turning in a circle and speeding up. And when we start to bring in torque and stuff, which we will do later, I think that's chapter 11 too, you may need to know what the total acceleration is. Okay, I think we can do this first problem here. So I'd like to do page 288, number 25. If somebody would just read through part A for us. Okay, so here's going to be my Earth. Here's my equator. Earth rotates around an axis that goes from the geographic North Pole to the geographic South Pole. Remember that magnetic north and south is not necessarily aligned with geographic north and south. And what you may not know, although Gianni, you may know from astronomy if you can remember, is that what it means to be at a latitude of 40 degrees north is that if I go from the center of the Earth and I draw a line out to the equator, and then I go from the center of the Earth and I draw a line out to that latitude, the angle between those lines is 40 degrees. It's good to know where it comes from and how you measure it. It's a life skill. You can do it using, well, you do it using the sun, and you measure the position of the sun at the same time from various places, and it has to be at the same time, and you do stuff like that. Okay. And in case you didn't know, the latitude at the equator is 0. Again, Gianni should have known that, but that's okay. So what do I want for part A? What does part A ask me for? So what do I want? What is it, Elisa? Omega. I want to find omega. Now, what do I know about omega for every part of the Earth? It's the same, because we're going to assume, although it's not true, that Earth is a rigidly rotating object. We'll forget about the oceans for a minute, okay? And any other nasty complications. So, what do you know about the rotation of the Earth? No, I don't need the radius of the Earth. Its period is 24 hours. Yeah, and if I'm talking about the angular speed, I want to know what angle it turns through, and it's going to go through a full rotation or go through 24 hours. And that's the wrong kind of hours, sorry. I confused my right ascension with my time. Okay. Now, would you ever give me anything in radians per hour? No. So how many, exactly, so how many seconds are in an hour? 3,600 seconds, okay? So as a decimal, so don't give me pi somethings. Use pi as 3.14. What do we get? We'll pick it up here tomorrow. In fact, I'm even going to save this doc.